Yesterday I was doing with this theorem. So we have done A implies B, we have done A implies C, we have done C implies B, and now the last part to complete the uh, chain for the equivalence of the conditions, that is B implies C. Okay.
सर जो आपने ऊपर वाले पार्ट में सेकंड वाला जो था बी इम्प्लाइज सी वाला
जी
सर उसमें जो सी डिस्कनेक्टेड लिखा था सर वो कैसे लिखा था
किसको डिस्कनेक्टेड लिखा था, कहाँ पर? अब आप लोग जो है
सर यहाँ पर ये है लास्ट में सी इज डिस्कनेक्टेड
दिस G is disconnected.
सी लिखा है ना आपने ये
Yeah, see, where is this? Yeah, this is. Okay. Class, what is the definition of, I mean, there are two things about connected and disconnected class. A set is, in fact, there are various ways of calling a set connected or disconnected. Now I am mentioning two statements. So please listen to both these statements very carefully. One of them I have used here. Here means to declare this, that is regarding disconnectedness, and one I shall be using today regarding connectedness. See, a set is disconnected if and only if we can find a proper subset of it which is both open and closed. Right? So because we showed that G is both open and closed and is a proper subset of C, so it means C is disconnected, which is a contradiction. Are you getting me? The result is, if you are in a metric space and if you are able to find out a proper subset of the metric space which is both open and closed, then the metric space will be disconnected. This result you must have done at the undergraduate level. At least the students, those who are from DU, they know this result. Right? Any one of you from DU? Do you know this result?
Yes, sir.
And if you negate it, so negation will be a set is connected if and only if it has no proper subset which is both open and closed. Is this okay?
यस सर
So if a set is connected, it means it has no proper subset which is both open and closed. It means the only open and closed subset of that set will be which sets?
empty and the set itself.
Very good. Very good. Who told this? Rahul.
Yes, sir.
Very good. So if a set is connected, then empty set and the set itself are the only sets which are both open and closed. So this statement I am going to make use of today. If you use its negation, if you take its negation, that will be about the disconnected. A set is disconnected if and only if it has a proper subset which is both open and closed. So this is something which you must have done at the undergraduate level, because at the undergraduate level I take metric spaces, so I do this result there in my class. Is this okay now? Can I proceed?
Yes, sir.
Can I proceed, Mamta?
यस सर
Okay. So I use this result actually. Okay. Just a minute, class. I'm just stopping the screen sharing. Yes, excuse me for a minute. Just a minute, class. Just a minute, class. One 64. Class, can you see the screen now?
Yes, sir.
Yes, sir.
Class, this is page number 157 from Shirali Vasudev. This is the book which we consult for metric spaces at undergraduate level in DU. Am I correct, Mamta? You are from DU, na?
Yes, sir.
Right? So we consult this book, yes or no? And
Yes, sir.
and if you know, this is just the second page of chapter 4. It is connected spaces, and you can see here. These are the equivalent criterias for disconnected. The following conditions are equivalent. This is disconnected, and you see at the fourth condition, class, there exists a proper subset of X that is both open and closed. Is this okay?
Yes, sir.
So the same thing I can say that metric space X comma D will be connected if it has no proper subset which is both open and closed. It means if a set is connected or a metric space is connected, then the metric space itself and the empty set, these two are the only sets which are both open and closed. Is this okay, Rahul? Mamta, is this okay now?
Yes, sir.
So अंडरग्रेजुएट लेवल की चीजें भी अब मुझसे रिवाइज कराओगे तो फिर आगे कैसे पढ़ेंगे? Okay, so let's start with this. क्या हो रहा है इसको? Okay, class, B implies A. So when I'm saying B, just a minute. Class, just a minute. Sorry, class. Uh, okay. Class, can you see the screen?
Yes, sir.
Okay. So, so what is given to us? Following is given to us that there exists a point A in G such that the value of all the derivatives of f at A is 0 for all n greater than equal to 0. When I say 0, it means, class, when you take n equal to 0, n equal to 0, 0th order derivative means the function itself. It means the value of the function itself is 0 at A. Is this okay?
Yes, sir.
Right? In class, what we are to show? We are to show that f is identically equal to 0 on G. That is, class, that is, we are to show that the value of f is 0 for all z in G. I'm writing this because someone of you yesterday was asking, sir, what is the meaning of identical equal? So this is the meaning. So let's start, class. So class, uh, I'm going to start with the following. Let us consider this set A. I'm calling this as set A. What is that? Take the take all those z's in G at which the derivative of the function is 0 for all n greater than equal to this. Class, please take a note. We are given that there exists a point A. Class, there can be more than one such points, yes or no?
Yes, sir.
Right. So we are taking all those points at which this phenomena occurs, where derivatives of all the orders are vanishing. So class, clearly A is non-empty. Why, class?
तो
Since
सर एक पॉइंट तो सर है ही हमारे पास.
एक पॉइंट है ना सर.
वेरी गुड. ए में है ही ना, ए के अंदर तो वो प्रॉपर्टी है ही ना, राइट? सो क्लास, लेट मी कॉल दिस एज 1. नाउ क्लास, let me first of all tell you the approach of our claim. I'm going to show that f is identically equal to 0. So let me tell you the approach at how we are going to show this. So class, actually I will be making one claim. Claim 1. The claim 1 will be that A is open. One again. Oh, this is one and the same thing anyways. Closed in G. The class, this will be my first claim. Class, then I will make one more claim that A is open in G. Right, class? Now class, remember, we are given that G is connected. So far we have not used this fact exclusively. It is given to us, class, in the statement of the theorem. Do you remember this?
Yes, sir.
Yes, sir.
Our G is open and connected.
Yes, sir.
So class, you know that. Then I will use the following logic. You know that since the final logic, this will be our final logic, final argument, will go like this. Since G is given to be connected, it cannot have a proper subset which is both open and closed, right? told you just now.
Yes,
Yes,
sir.
sir.
है ना? So
Yes, sir.
if G is given to be connected, therefore, by definition of connectedness, the only sets in G which are both open and closed are either the empty set or G itself. Is this okay, class?
Yes,
Yes,
sir.
sir.
Yes,
So
sir.
therefore, now this is open. I'm saying that the only open sets which the only sets which are both open and closed are empty or G. Now we in claim 1 and 2 we are saying A is both open and closed. So therefore, either either A should be empty or A should be G. But point number 1 says what?
Yes,
This is not possible.
Yes, sir.
Not possible
sir.
in view of,
A is non-empty.
right? Because A is non-empty. So it means A is G, right? Is this okay?
Yes, sir.
And class, if A is G, then it means what?
A is connected.
No, no.
F is identically zero.
Yes, yes. Now you see, if A is G, then C class. What was A? A was the collection of all those Z's in G where the where all the derivatives of F were vanishing. And class, take a note here, it is equal to, right? So now you combine these two informations.
Yes, sir. Identically zero जाएगा sir.
Yes, you combine these two information, and these two informations are telling you if you take n is equal to 0, it means you can say that this that this set was the collection of all those z's where the function was also taking value 0, because when n is 0, it means the function. It was the collection, it means A was the collection of all those points where the function f itself was taking value 0. Yes or no?
Yes, sir.
But now we have shown that A is nothing but G. That is, it means what? That is, it means function is taking value 0 at all the points of G, because A and G are same. And it means what, class? It means f is identically equal to 0 on G. Yes or no?
Yes, sir.
So this is what exactly we are supposed to show. Is this clear, class?
Yes, sir.
Yes, sir.
So now we are finally left with what? To make the claims A1, to make the claims 1 and 2. Is this okay?
Yes, sir.
And the proof will be complete. So let's make the claim number 1.
Yes, sir.
Claim 1. Okay. Class, to show that, so claim 1 is to show that A is closed in G. So again, class, there are various ways of showing a set to be closed. So the way which I am going to use here is the following. I am going to take a sequence in a convergent sequence in A, and I will show that its limit is also in A, and that will claim, or that will establish, that A is closed. Is this okay, class? I will be using this approach. It means every convergent sequence in A is having its limit in A. So that is sufficient to declare that A is closed. Is this okay?
Yes, sir.
Okay, fine. So this is the idea of closeness in terms of sequences. I mean, class, all this is undergraduate stuff from metric space theory. So this is what exactly I'm going to do. So let Zn be a sequence in A such that Zn is converging to some Z. So our aim is we will show that Z is in A. And once we have shown that Z is in A, then it will, and this will imply that A is closed. Okay, class. And to show and to show that class Z is in A, what do I need to show? I need to show, that is, we should show that the derivatives of all orders of f at this point Z. Class, if you want, you can call it Z naught maybe to make a distinction. This is 0 for all k greater than equal to 0. I need to show this because this is the property of the elements which belong to A. A is the collection
Yes,
of A is the collection of such elements only, right? So I will show this. Now see, class, since f is analytic, it is given, class, in the statement of the theorem. It is
Yes, sir.
infinitely differentiable. We know that every analytic function is infinitely differentiable. And if it is infinitely differentiable and all the derivatives are continuous, automatically they will be continuous. Because if it is differentiable twice, it means first order derivative is continuous. Yes or no, class? If it is differentiable
Yes, sir.
thrice,
Yes, sir.
it means, so whenever you take next order derivative, the function up to the previous order derivative will be automatically continuous. Whenever you say that f dash exists, this automatically mean that f is continuous. Yes or no, class? You just go on repeating this. If you say f double dash exists, it automatically says that it means derivative of f dash exists. It means f dash is continuous. Is this okay? Very easy to understand. Is this okay, class?
Yes, sir.
yes, sir.
Okay, fine.
Yes, sir.
So what I am trying to say is this, that is, this function fk, all order derivatives of f, they are continuous for all k greater than equal to 0. Is this okay? Right, class?
Yes, sir.
Therefore, now I start with this, what I exactly want. I'm start, oh, Z1, sorry. So class, this will be, sorry, this is the notation for kth order derivative. Class, Z0 is this. Is this okay? And
Yes,
now
sir.
I hope you must be getting what I'm going to do. I'm going to use the continuity. Continuity allows me to take the limit outside. Is this okay?
Yes.
Yes,
And
sir.
because all these ZNs were in A, it means the moment I said that these ZNs are in K, it means automatically that the values of all orders derivatives of f at all these ZNs is 0. Because certainly they will satisfy the property of being in A, na? If they are elements of A, then certainly they will satisfy this property. Yes or no?
Yes, sir.
Yes, sir.
So all these are 0. So this is simply limit n tending to infinity of 0. All these are 0 because, and it is 0. And certainly this is for all k. Greater than equal to 0. Is this okay, class?
Yes, sir.
Yeah, so that is what I have shown. That is, I have shown exactly what I wanted to show. That is, I have shown this. Yes or no? You forget all this intermediary, na? I'm writing the final thing now. Is this okay?
Yes, sir.
And hence done now. The aim is done. This is what we wanted to show. Yes or no?
Yes, sir.
So once the aim is done,
Yes,
it will
sir.
claim one is done. Is this okay?
Yes, sir.
So thus
Yes, sir.
claim one is done. So now let's make the claim two. Claim two is to show A is open in G. And to show that A is open in G class, I simply need to show that if I take an arbitrary element in A, then there exists some neighborhood of A. It means some upper bound around A having some radius. Of course, radius is always positive, so that it fully sits inside G. Yes or no, class?
Yes, sir.
Right? So I am to find out.
Yes, sir.
So let me start with an arbitrary element, and I am to find out this R actually. I am to find out a ball. Finding R means to find a ball which completely sits inside G. Once it is shown, then it will be clear that A is open. So let's see how I am going to show you this. So class, you take any R greater than 0 such that sorry class, sorry. Class, note that A is contained in G, yes or no? Class, because A is nothing but the collection of elements from G satisfying a certain property. See here, A is collection of elements from G satisfying this property. So certainly this will come out to be a subset of G, yes or no?
Yes, sir.
Basic set theory.
Yes, sir.
Yes, sir.
Good. Thus, the small a which I have taken in capital A is also in G as well.
Yes,
Is this
sir.
okay? But class, don't forget. But we are given that G is open. It is given, na?
Yes, sir.
If you remember, in the statement of the theorem, we are given that G is both open and connected. Yes or no?
Yes, sir.
Therefore, using the definition of an open set, therefore, there exists a ball around A fully sitting inside G. Is this okay, class?
Yes, sir.
Class, I will be showing you. I will be showing that actually BAR, this ball itself, is the ball which I am looking for. I will show you that this ball is actually sitting inside A. सॉरी क्लास, या ए को ओपन दिखाना था तो ए में दिखाओगे ना बॉल को, सही, ओपन जिसको दिखाना है। सो सॉरी, so I will show you that this is actually the ball which will serve my purpose. Is this okay, class?
Yes, sir.
Okay, good enough. Now class, F is analytic on BAR, right? Because it is analytic on G, so it will be analytic on this ball also. Is this okay? Therefore, we can write a power series expansion
Yes, sir.
for Fz. We know this now. For all those jets which are in this ball, yes or no?
Yes, sir.
We know this now. And where an is nothing but, we know this also, that how these coefficients are defined, right? Is this okay? कोई कुछ कहेगा?
Yes, sir.
Is this okay?
Yes, sir.
But
Yes,
take a
sir. Yes,
note. But take a note. What is given to us, class? This A is not an ordinary point. This is the point with which we started, right? Right, class?
Yes, sir.
Right. So all these F and A's are 0.
0.
So yes,
0.
this is by the given fact, right? By the given fact. Is this okay?
Yes, sir.
Yes, sir.
And class, if all the coefficients are 0, then this means what? It means
FZ is 0.
yes,
FZ is 0.
Z in BAR. Is this okay? Is this
Yes,
okay?
sir.
ठीक है? And now class, take a note. What was the part? What was the part A implies B, class? If you remember, what was A implies B, class? A implies B was that if F is identically equal to 0 on G, then this implies that there exists a point A in G such that the derivative
Is
of
0.
all orders of F
0.
at A will be 0. Yes or no?
Yes, sir.
yes, sir.
Class, what is G? G was open and connected set. Yes or no?
Yes,
Yes, sir.
Yes, sir.
sir.
And F was defined on G and F is analytic. Yes or no?
Yes.
Yes.
Now
Yes.
please
Yes, sir.
take G is equal to BAR. Now you can see that BAR is satisfying all the properties. It is open ball. Class, open ball is connected as well,
Yes, sir.
Yes, sir.
right? It is. I think I explained you in the class that just with the help of a straight line segment, you can connect any 2 points in the open ball. And now, because F is analytic on G and this ball is contained in G, so it means the function will be analytic at this ball also. Yes or no? This is a part. This is a
Yes,
part
sir.
of G, na?
Yes,
So
sir.
now I am considering this ball itself in place of G for some time. And now, class, don't you think that this is A now?
Yes, sir.
Yes, sir.
So, according to part A implies B, what do I have? Tell me.
There would exist some
It is a point A.
Yes, you are right. You are right. You are right. And in fact, class, not only this. In fact, if you recall, there exists not only this. If you recall in the proof of, we observed that this phenomena will be for every Z.
Yes, sir. For every
Do
Z.
you remember this?
Yes, sir.
Do you
Yes,
remember
sir.
this? We saw
Yes, sir.
that there is no particular. In fact, you take any Z, this phenomena will be observed. Do you remember the proof?
Yes,
Right?
sir. Because that was argued.
Yes,
That,
sir.
Yes, sir.
that's why I gave you the proof. That was the main purpose of the proof, so that you could see. In fact, I explained you yesterday that we get this information for every element of G, this information. So that's a point that to do the other parts, we require this information only for one point. That's a different thing. So it means, class, I can say that f and z will be 0 for all n greater than equal to 0 and for all z in BAR. Is this okay, class? Yes or no? Is this okay, class?
Yes, sir.
It means, class, what? It means, class, don't you see, that is all the, now you see, points of BAR are satisfying class. You should also take a note of my language, that sometimes how do I write and how do I speak, so that we may understand the meaning properly and clearly. Now, that is all the points of BAR are satisfying the property. This, I'm writing the same thing, class, in words only. Yes or no? This thing
Yes, sir.
I'm writing, this thing I'm writing in words. That's why I have written that is. All the points of BAR are satisfying this property. And if, class, any point satisfies this property, then it means that point must be there in A. Because what was A? A was exactly the collection of all those points which were satisfying this property. Yes or
Yes,
no?
sir. Yes, sir.
And
Yes,
now,
sir.
now I have shown you that every point of BAR is satisfying this property. It means what, class? That
Ball
is, it means
BAR
this
is
whole
contained.
this whole
BAR
of
is contained.
BAR is sitting inside A.
Yes, sir.
This complete ball BAR is sitting inside A. Every element of this ball is in A. Yes or no?
Yes, sir.
And now it means what? It means A is open. Thus,
Open.
yes,
Yes,
we were to find out a ball around A, which fully sits inside A, and I have shown you that. And now the proof is complete. Rest of everything I have already explained you.
Yes, sir.
Is this okay?
Yes, sir. Yes.
Yes, sir.
Okay, fine. At least I am happy that I am able to complete this proof. Okay, class. Now a few consequences of this theorem. Now the very first consequence. Now let f and g, these be two functions defined on C and both are analytic. Class, then f and g are identically equal. Class, two functions are said to be identically equal when
If their values at all
The
points in
images are
yes,
same, sir.
their values at each and every point of the domain, they
Are
have the
same,
same
sir.
value. Yeah, coincide. Good. So f is, so we so class, we have to show that they are identically equal if and only if this set, the collection of all those elements in G, such that this set has a limit point in G, has a limit point in G. So class, One is the definition, and now we are going to show this with the help of this. Actually, we are having a criteria for the equality of two analytic functions. So the two functions are analytic if and only if the set at which both of them are equal, that set has a limit point in G. So if you want to check that whether two functions are identical, what you do, you need not check their values, whether their values are equal at each and every point. You simply pick up those points only where their values are equal, and that set has just one limit point. If you are able to pick up such a set, then you can at once declare that the functions are identically equal. Is this okay, class?
Yes, sir.
So that's the power of this result. So see the proof. The proof is very easy, just one line proof.
We will define some H.
Oh, very good. So let us define some h is equal to f minus g. Is this okay? Now class, then h will be identically equal to 0 if and only if the set z in G such that hz is equal to 0 has a limit point in G. Class, where from we have got this? From the above theorem. In the above theorem, we saw this. H identically equal to 0 is A, and H and this is nothing but C. The right hand side is nothing but C, if you recall. Yes or no, class?
Yes, sir.
Yes, sir.
Right? Or you can say, in class, Hz means simply f minus gz. And class, uh, I'm sure you know how to define the addition and subtraction of two functions. This means fz minus gz. This is how we define the difference of two functions. So class, we can simply say, or saying h identically equal to 0 means class f minus g identically equal to 0. Or I can say that f identically equal to g. Is this okay, class? I take the value of h to be f minus g. Is this okay? So if and only if, so this is just one line proof. G such that instead of hz you simply write fz minus gz, and I will be taking gz on the right hand side. Is this okay, class? Is it limit point in G? Is this okay? So it is a direct consequence of the above theorem. Is this okay, class?
Yes, sir.
So I took h is equal to f minus g just to make you understand it easily. That's it. Otherwise, as such, there was no need to take h. You could do it straightforward. Just a minute, class. What's happening? Okay. Now, class, another consequence. This is really very nice, class. It tells us that every zero of an analytic function has finite multiplicity. That's a very nice result. Every zero, any root you take of an analytic function will always have finite multiplicity. So this is, I can say again, a corollary, again a very nice implication of the theorem. So it is following. Class, suppose class G is open and connected, and F is defined on G. F is analytic class, and also one more information which is given about F is that F is F is not equal to, what is this? sorry, class. Mhm. In class, it is given to you that f is not identically equal to 0. F is not identically equal to 0. Okay. Now further, let not identically equal to 0 means class that f can't be 0 on the whole of set G. There may be 1 or 2 points where f is 0. That's a different thing. But it cannot vanish at the whole set G. So class, let A be some point in G such that the value of f at A is 0. Suppose कि एक पॉइंट ऐसा है जहां पर A की वैल्यू 0 है. So class, this corollary says then there exists an integer n greater than equal to 1 and an analytic function G, which is analytic on capital G, such that G will not be 0 at this A, at this particular A. And fz will be equal to z minus a to the power n into gz. It means class that this A can be of multiplicity n at the most. There will exist an integer. Such an integer will exist. So the root A, and because it is given that the value of G at A is not 0, so it means G is, this A is root of f of multiplicity at the most n. So let me write it in short form. That is actually, the result is saying that each 0 of f, because class here I took an arbitrary 0 of f. I took an arbitrary 0. So certainly if this thing holds for 1 0, so it will be applicable for every 0 or every root of the function f. Is this okay, class? Because I took an arbitrary root. Is this okay? So that's why I'm writing each, or you can write any. You take any root of f will have finite multiplicity. Is this okay, class? Is this okay, class? So let's start with the proof. Class, recall the part A implies B of the previous theorem. What that says?
F is identically equal to 0 implies that.
Yes. If f is identically equal to 0, that implies that there exists some point A in G such that the
Where Fn is
derivative
0.
of all the orders
0.
will be 0. Right, class? Is this okay?
Yes, sir.
Yes, sir.
Yes, sir.
And class, these are if and only if actually. Through some root, they are actually if and only if, right?
Yes, sir.
You know this. So let's not go into that route. So in fact, they are if and only if. So class, we are given that f is not identically equal to 0. We are given this, class.
Yes, sir.
Yes, sir.
And if f is not identically equal to 0, class, then certainly this phenomena cannot happen for all n's. This phenomena will have to stop at some stage.
Yes, sir.
Yes,
because,
sir.
because this and this, these two conditions are equivalent na class, this condition and this condition, they're equivalent.
Yes, sir.
So if f is not identically 0, then certainly there will be some n that the derivative of f of that particular order, the value of the derivative of f of that particular at a, the value will not be 0, right?
सर जो सेकंड का नेगेशन होगा सर उसमें सर एन किसी एक पर्टिकुलर एन पर सर जीरो नहीं होंगे या कोई एक ऐसा एन एग्जिस्ट कोई एक पर्टिकुलर ए ऐसा एग्जिस्ट करेगा जिस पर सर ये कंडीशन होल्ड नहीं होगी.
और सेकंड का नेगेशन का मतलब मैं समझा नहीं.
मीन सर इफ ए इज डज नॉट इंप्लाई मीन सर इफ ए डज नॉट मीन सर ए कंडीशन इज नॉट ट्रू. सो सर जो बी कंडीशन है सर
देखिए जब आप इफ एंड ओनली इफ जब आप इफ एंड ओनली इफ कहते हैं तो इफ एंड ओनली इफ का मतलब है कि अगर आपका लेट अस से आई कॉल इट नंबर 1 and I call it number 2 condition. So if and only if means if 1 holds then 2 will hold, and if 2 holds 1 will hold, and it also says that if 1 does not hold 2 will not hold, right?
Yes sir.
Right, so here you don't have a negation kind of thing. So it means simply that if you don't have 1 you don't have 2. So if you don't have 1 then you don't have 2 means what? You have to understand that it means there exists some a at which derivatives of all orders can't be 0.
Yes sir, ठीक है.
And if derivatives of all order can't be 0, it means there will be some stage at which the derivative will be non-zero. Is this okay? So I am going to use the theorem in this way. Is this okay, class?
Yes sir, ठीक है.
So since f is not identically equal to 0, therefore by the theorem, and class this was precisely theorem 3.7 in your book at page 78, there exists some n some k, I am saying class it greater than equal to 1. Class take a note, I am not taking 0, that you will see why, such that the value of this at a is not 0. Because if I take k is equal to 0, then we are already given that the value of f at a is 0. This we are already given. So certainly we will have to exclude the function itself. So that's why I have started k from 1. We can't take k from starting from 0, because if you remember, you notice here the range of derivatives starts from 0, right? It means the function is also included. But we have to exclude the function because it is already given to us that the value of the function at a is 0. Is this okay? So certainly this k will be bigger than or equal to 1. Is this okay?
Yes.
Okay, fine, good enough. So there exists some k. Now class, we are saying that there exists some k which is greater than equal to 0 and at which the derivative is non-zero. Now class, it is quite possible, suppose the value of f, the third derivative of a is non-zero, but the value of sixth derivative again becomes 0. Then the value of eighth derivative becomes non-zero. We may have something like this, now, because if you notice this statement is only saying that there exists some k such that fk at the kth order derivative at a is non-zero. This is telling us nothing about that what can happen to the other order derivatives after k. Yes or no, class?
Yes sir.
It is just saying that there exists some k. So class, what we are going to do to handle this situation, let n be the largest integer, of course greater than equal to 1, such that such that f at a is 0. This we already know, it is given. First order derivative at a is also 0. Second order derivative at a is also 0. Dot 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 dot, and this. But this is so. Let us focus on this only. Then you forget about the others. You forget about the others. Then we don't know. So we locate that n, the largest n, where we get that derivative is non-zero. Is this okay, class?
Yes, sir.
Okay, fine, good enough.
क्या उसके पहले के डेरिवेटिव जीरो ही रहेंगे?
No, I'm not saying this. So, uh, uh, you see, do you agree with this that derivative, the value of f at a is 0? Do you agree with this?
Yes, yes.
So then we take first order derivative. Now it may be 0 non-zero.
Yes, sir.
Are you doing some mistake?
Actually, okay, I got it. A
Yeah.
is the multiplicity of n, so it will be.
Yes. Try to understand that. No, but still you have created some confusion. So I want to be clear in myself. So that is okay. I will be showing you that this n is going to be the multiplicity. That's a different thing. But I should be clear in myself now that what I am going to tell you. Uh, uh, just a minute, class. Uh, no, class. Actually, you should not think it this way. You should think it this way. Uh, no, I'm doing right. I know this, that I'm doing right. Now the point is how to explain it to you in a better way. Okay. Uh, okay. I'm actually saying this, class. Let n be the largest integer such that the derivatives of first order, second order, and up to n minus 1th order are 0. I am saying it this way. Is this okay now?
Yes, yes, sir.
So wherever up to I can go, let us say uh, I can, for example, I am having derivatives up to 4th order to be 0, right? So now it's the correct way to put it. So just go on looking at that up to which stage you get the the values of the derivatives to be 0, right?
Okay, sir. Okay. Got it.
Then certainly, class, there will be a stage where derivative will be non-zero, because if this trail goes on, if you get on and all orders derivatives come out to be zero, then it means what, class? Then this will actually imply that f is identically equal to zero, which is a contradiction. So this is not possible. So certainly there will be some n where the derivative will be non-zero, yes or no? So when I am saying n be the largest integer greater than equal to 1, means should we write largest or
Smallest लेंगे
yes,
तो
smallest?
right.
Oh, I think smallest will be the appropriate terminology. Sorry. Yeah, that's why the confusion. Oh my God. Is this okay now? Let n be the smallest integer, so that up to this stage the derivatives are zero, and after that stage it is non-zero. And now after that you may get somewhere it is zero, some maybe some derivatives will be non-zero. That's a different thing. But we are very sure that certainly we will get some n of this type at some stage, because we can't go on and on. Is this okay, class? Is this okay now?
Okay, sir.
Yes, yes, sir.
It's okay now.
Yes.
I'm sorry. I'm sorry. Yeah, that was a genuine confusion. That was a genuine. Yeah, it's okay now. So you just go on looking at up to the derivatives up to where the derivatives are zero, and then certainly there will be some order derivative which is non-zero, and you stop at that stage. Is this okay? After that, you don't need to look into whether the derivatives are zero or not. But there, we have the guarantee that certainly there will be some n where the derivative will stop getting zero. Because if it is zero on and on, then that will amount to saying that f is identically equal to zero in view of the theorem, which is a contradiction to the given fact. Is this okay? Now it's okay. Is this okay?
Yes, sir.
Yes, sir.
Yeah, sorted. Good. So class, I think we should stop here now, because still uh, this proof is quite lengthy and it may take around another 10 minutes. So let's stop here. And on Tuesday, I will continue with this proof, and I will be taking up the last, most important, one of the very important entities of this section, what is called as the maximum modulus theorem. Okay, so let's stop over here. Thank you. Oh, okay, just tell me who got confused because of this
Me, sir, Ashish.
this largest?
Sir, Ashish.
Ashish, okay, good. Thank you. Confusion is good. I mean, if there is a confusion, there is a confusion. If the things are clear, then you don't have a confusion. Okay. Just a minute. Just a minute, class. Sorry. What is happening to this? Just a minute, class. Okay, class. Thank you very much. I have taken your attendance. Now we will connect on Tuesday.
Thank you,
Thank
sir.
you, sir.